All right, everyone. We're going to dig into part 2 of module 3. In this specific case, we're going to be looking at crystal direction. And so in this little mini segment, we're focusing on how to determine crystallographic direction at the unit cell. So we'll start with that. At the unit cell. 2, we're going to start thinking about the steps to convert a vector into a directional indice, so UWV format. And then last but not least, how crystallographic directions work in a hexagonal crystal. So, as always, if you have any questions, it's useful to consult your book. I believe that this can be found on page, let me double check, I believe it's 80 or 70, 75, right? We're looking at section 3.13. So I'll just put Anyways, so when we're looking at crystallographic direction, a crystallographic direction is a vector that describes the line between 2 points in a crystal lattice. This is useful because it will help us describe atomic arrangements, slip directions in metals, and material behaviors like strength and continuity. To define a crystallographic direction, we use a set of 3 indices, right? We're using U, W, or U, V, and W, which represents the normalized vector in X, Y, and Z directions. We determine these indices, right, the UWV, UVW format, by using a fairly concrete step-by-step process, which we'll run through here. So, number 1, right, we are choosing a right-handed coordinate system. So this is, and then we have to determine the coordinates of the vector system. Yes. Let me just double check on this. So in step 1, we're looking at, do we have an X, Y, and Z axis that are all, oh my goodness, that's terrible, aligned with our unit cell, right? And so, again, we're thinking about it in terms of X, Y, and Z. And then our unit cell would fit directly into there, right? But we want to make sure that that aligns with the edges of the unit cell. We place the unit cell at the corner of this intersection for our convenience. And the next step is to identify 2 points in the direction vector, right? And so, generally speaking, for the next couple of examples, we'll be starting at the origin and then within the context of the unit cell, right? We'll be drawing a line from the origin to somewhere within the unit cell, right? And so let's say we end up there. And so that will be how we sort of, number 2, identify 2 points, the origin and then the endpoint, which we'll call the head and the tail in the vector. And so the direction is defined by what I said before, the head vector, right? And then the tail point. Let's use a different color. Tail, which is going to be, let's see, x1, y1, z1, and then the head point, which is going to be x2, y2, z2, right? And so, for example, we may have, this will be 0, 0, 0 at the corner, right? And we may be moving towards, I don't know, for instance, 1 half, and then let's say 1/4, which would be like up here. Those are our heads and tails. Next, you are going to subtract the tail point coordinate from the head point coordinates, right? And so what this means is that you are going to compute the differences, right? So we're looking at x2 minus x1, y2 minus y1, z2 minus, that's too messy, z1. And so for our example, right, that would end up being, yeah. So you think about it like that, our head coordinates, what are the differences, and then you drop those down, and then you start step 4, which in this case, here, let's bring this up a little bit. Where we normalize the coordinates differences using a lattice parameter, right? And so you're going to divide each difference by the perspective lattice parameter A, B, C, assuming that A is equal to B, which is equal to C, which is equal to 1 for a simple cube, right? And so, yeah. And so this would end up being, 1/1 yeah. And then second to last, we would then multiply each value by the common factor to get a whole number, right? We want no fractions. So then we would multiply everything by the lowest common denominator. In this case, right, you can see, where our head is 0, 1/2, 1/4. The lowest common denominator there after you subtract everything is in quarters. And so right there, we would make sure that we would multiply everything by 4. And then last but not least, we want to make sure we write it in bracket notation, right? And so with bracket notation, you will have boop, 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 and then your 3 values in final notation, which is U, V, W notation, enclosed in square brackets. So as we move through, think about an example here, right? Let's say we take this one right here. We have a little box, Now we've got our vector. Let's say this vector is about halfway up, so it's going to be 0.5. So number one, we've determined our coordinates of the vector and the tail. Our tail vector, boop, boop, boop. Tail vector is equal to 0, 0, 0, because right here we are at the origin. Our head vector, our head point right on the vector is right here about halfway up, and so this is going to be a 0 c over 2. So the next we are going to subtract our tail coordinates from the head point coordinates, and then also normalize the differences in terms of the lattice parameter, right? And so with this situation here, we're looking at, let's see if we can move these up actually. Oh, no, I do not want to do that. Bring that up. And then we'll bring that up. Now we're looking at head minus tail over the parameter, which is equal to a minus 0 over a 0 minus 0 over b, and then c over 2 minus 0 over c, which is then going to equal 1, right? Because this is going to cancel, and then a over a is 1. 0, because 0 divided by b is going to be 0, and then 1/2, because, c over 2 divided by c is equal to 1/2. Now we reduce the integers. So I'll make this smaller. Two, 0, 1, because we're multiplying everything by 2, and then we'll hit everything with a bracket, and that'll give us 2, 0, 1. And that's it. Pretty straightforward.